All right, now that we've looked at uncoded modulation and all its problems, let's start looking, at least from a theoretical perspective, at what coding can and cannot do. So, why are we looking at coding? We remember the key lesson from the previous section is that with fading, uncoded modulation is very difficult to provide any reasonable level of reliability. Just as a quick refresher, we plotted in that previous section the uncoded symbol error rate even on QPSK, and we see that there is a huge gap between the performance on an unfaded channel and a faded channel. So we need to do channel coding. And what is channel coding? The key idea is to not transmit one bit or one symbol at a time, but to transmit in blocks. And these blocks have redundancy. And what that means, if that some parts of the block fails, you could still recover from unfaded parts of the block. And that is what will provide the reliability that with coding. And just as I stressed in the last section, all commercial systems, wireless systems, always use channel coding. All right, now to understand when and when not channel coding can work, I wanted to look at two kind of extreme, very idealized cases. So the first case is what you could call the slow fading case. So this is the idea. You have a transmitted wireless channel that's fading in and out, and I transmit on a block that's very small relative to the variation of that channel. Or if, for example, if this was over time, we'd say that the block length is much shorter than the coherence time. Now, in this highly idealized model, what's happening is that all these symbols in that block are fading equally because the channel is basically flat over that block. And we will see that the performance can be measured by what's called an outage probability or an outage capacity. But in this case, we're going to see coding will not buy you much. And that intuitively makes sense since all the parts of the block fail together. You can't benefit from the redundancy that coding has. On the other hand, the other extreme is what you could call fast fading, where the block length is much larger than the coherence time, as I've shown here, meaning that there are many independent fades during that transmission. And that would either mean you're transmitting much larger than the coherence time or much larger than the coherence bandwidth. In this case, we can achieve something called the ergodic capacity, at least theoretically, and this will be much, much better than what we would get with uncoded modulation. So these two ideas in mind, let's start our analysis on slow fading. So as we said, in slow fading, we have a channel and the coding block channel is basically constant over the coding block. So it sees one single SNR, which I'll denote by gamma. All right, and so the SNR is constant, but it varies over different blocks. And this means that the transmission time is much shorter than the coherence time if these were variations over time. Now, let's say that code has some target SNR, let's call it gamma target, and let's assume that we have some distribution of the SNRs, some probability distribution. So then all I would do to analyze this is it would define something called the outage probability, which is the probability that your SNR does not meet your target. So that's a pretty intuitive idea, and I'll give you some examples that you can work out. Let's just look at what happens in a Rayleigh fading channel. So in a Rayleigh fading channel, remember that the SNR is exponentially distributed around its mean, which I'm going to denote by gamma bar. So the outage probability for a given gamma target is just the CDF for the exponential, which is this exponential term here, as you could remember from probability. And then if you wanted to solve for the average SNR you need to get a target, you get this expression. Now, at very low outage probabilities, say like 0.01, just do some quick mathematical manipulations, and you get that the ratio of the average SNR to the target is by basically 1 over P out. Or in other words, if you wanted, that means the average SNR has to be greater than the target SNR by this amount minus 10 log 10 of P out. Let's just give you an example to make that more concrete, because that was just a bunch of math. All right, say your target SNR is 10 dB, all right, and I want to make sure that I can get 10 dB 99% of the time. Not that reliable, actually, because many applications need much more reliability. So in other words, I want an outage probability of 1%. So I just use my formula from the previous slide. And it says the average SNR has to be my target plus this factor. There's a minus sign here. And, well, of course, log 10 of 0.01 is 20. So we get 20 extra dB or 30 dB of SNR. Now, what does that mean? Or let's just first actually let's look at it on the graph just to make sure we all see what we're doing here. What we have on the graph is this fade, which is the drop in SNR. And I want to make sure, this is the probability of that drop, so I want to make sure that that drop of SNR is less than what drop occurs with a 1% probability. And with a 1% probability, you have a 20 dB drop. Now, what does that mean? It means we have to add 20 extra dB. So normally you'd be coming in at 30 dB, but you can only, with 99% reliability, get 10 dB. So you're adding an enormous amount of extra power to overcome and get a more reliable channel. All right. Another way to think about it is look at something called the outage capacity. It's just basically a mathematical manipulation. It's the same idea. All right, you have some, say for every SNR, you have some rate that you can achieve. So that will depend on, your coding and modulation scheme and how reliable they are and so on. And we'll assume, again, that the SNR is random because it's fading. So that means that the rate is also random. And I could say, well, what's the outage capacity? And it is the rate I could get with a certain reliability. So I want to make sure that the rate is less than my target rate with only some rate P out. Now, again, just to make it concrete, let's take a look at some numbers. Suppose your system has 20 megahertz of bandwidth, and you can get about 60% of Shannon capacity. Remember, that's kind of very close to how LTE is. And to say the average SNR is about 20 dB. So what's the outage capacity if I wanted 99% reliable with Rayleigh fading? Well, it's again pretty easy to compute. Remember that the SNR that you would get with a 1%, 99% fade will be the average minus this expression. And if it's 0.01, that will be 20 dB. If it was 0.001, it'd be 30 dB. All right, and just it grows every decade. All right, so that means with 99% of the time, if I wanted 99% reliability, I have to add in another 20 dB. So my average SNR of 20 goes down to 0 dB, or in linear scale, it's 1, which means that the outage capacity I'm going to get is about 60% of the Shannon, which is 12 megabits per second. But what would I have got had I had the average SNR? I would have got, well, 20 dB. 20 dB in linear scale is 100. If I plug that into the Shannon formula, I get 80 megabits per second. So on average, this channel could have gotten 80 megabits per second. But if I want to be 99% reliable, I am way down. I'm down to about 12 dB, about 1/7 of that rate. So I've taken a huge penalty to make this reliable. So what are the implications for outage? It's really this, that if you have snow fading, like Rayleigh fading, you need to add a very large fade margin. The channel coding is not getting you around this, and that's pretty clear why. It's because all the bits in that code fail at the same time, so the redundancy doesn't help. Now, you still probably, if you are adding fade margin, you have slow fading, you want to add channel coding anyway, because it will be very useful for averaging out or giving robustness against noise, which is typically independent across symbols, but it's not going to get you around fading. Now, you don't really have a choice of whether your system, or not much, system points whether it's slow fading or fast fading. So you're going to ask the question, what can I do if you have slow fading? Well, we're going to talk about some solutions in the next unit, but there may be a way around even if you're in this slow fading channel. For example, if there's motion, maybe we can just retransmit later. Or maybe we can adapt the rate to something that uses less SNR, or maybe sometimes we just have to accept that some of the time or some of the locations are going to be an outage. Do not despair, there are techniques. We're going to talk about them in the next unit, but right now I want to go on to fast fading, which is where coding really shines. So in fast fading, remember that coding block is much longer than the coherence time, or much longer than the coherence bandwidth. You have many independent fades across that block. So here's a very simple model to kind of look at the most extreme version of fast fading. You have your transmitted symbols S of n, and you have your fading gains H of n, and we're going to assume these IIDs. So it's varying so fast that every symbol you're getting a new fade. But remarkably, somehow we're going to assume that the receiver can track it. So that obviously becomes an issue if you have a fast fading channel, and we'll talk about that when we go to equalization. But let's just assume for now that this channel is miraculously tracked. All right, and we're going to also assume that the block length is very long, or to be precise, infinitely long, right? And that will allow us to model the effect of these independents. All right, so we kind of implicitly assuming large block length and that we have many independent fades. All right, under this model, we have our fast fading model with these IID gains. We can define something called the ergodic capacity. It's a purely information theoretic concept, which is just this. What is the maximum rate per symbol I could get under some power constraint? And I mean maximum over all possible codes, block lengths, and no computational limits. I will get into how to do these things practically momentarily, but I just wanted to look at what is theoretically possible now. And it turns out that this theoretical ergodic capacity is actually easy to compute. All right, is just this expression, and if you note inside this expression is none other than the Shannon formula, and there should be a bandwidth out here, the Shannon formula inside here, but there's an expectation, and the expectation is over the random SNR. So you just, for each possible SNR, you compute the capacity of that SNR and then just average it. It's like you had a bunch of independent channels and then you just put your power uniformly across that. All right, before we go on, I just wanted to look at some key remarks about this very simple formula. First of all, remember this is a theoretical result. It only in principle holds when you have infinite computation and delay. You don't, of course, have that. We're going to look at the performance over real codes next, but you'll see that actually even in those codes, we're going to do pretty well with channel coding. Now, the other interesting thing is that the transmitter doesn't even have to know H. Well, the receiver absolutely needs to know that, and that's going to be a whole unit about estimating the channel, equalizing the channel, but the transmitter does not need to know it. In fact, you can use the same code that it did on the flat channel, basically a Gaussian code. Now, if the transmitter knew the channel, it actually could do theoretically a little higher. There's a game called water filling, and what it would do, ideally, is redistribute the power to the periods in time or symbols which have a better SNR. It's just a little bit of an optimization. It's not that hard to work out, but it doesn't in practice have much value, so it's not used that often, so I'm just going to skip it. But check it out. It's in Andrea Goldsmith's book, for example, and several other texts. The idea is called water filling. All right. What I want to do is just look visually at this, what this looks like, this ergodic capacity. So one thing about it is that the ergodic fading capacity is always lower than the flat channel capacity. And the reason here is that if you take the capacity as the expectation of a log, but the expectation of a log is always less than the log of an expectation. That's from a math term called Jensen's inequality, because log is concave. And this is the AWGN capacity with the same average SNR. And indeed, if you plot, for example, the AWGN capacity here, the blue line, and the Rayleigh fading line, it is a little lower for every possible SNR. But that gap is not that large. at least at sort of moderate spectral efficiencies. For example, at a spectral efficiency of 1 bit per second per hertz, that gap is at about a dB and a half or something like that. It's not that bad. It's much, much better than what we had with fading channels. And even at higher order modulation, like 2.5 bits per second, here we're maybe 1 to 2 dB. So conclusion is we should try to code over a large number of independent fading realizations if we can, and at least in principle, theoretically, that capacity loss is relatively small and much, much better than what you would get with uncoded modulation. I'm going to look at practical codes next, but at least this gives us an idea about what's achievable. All right, with that, before we go on to talking about practical codes, I just want you to work out the outage capacity in an indoor environment. So this is a little bit different than what we had, but not too much of an extension. Here you have two variations. One is coming from the distance-based path loss. You're looking at users in a room, and that would be kind of large-scale fading. And then you have on top of that some small scale fading. So if you look at the distribution and you're going to generate this plot, you'll have a distribution of rates, which is what happened with the large scale fading variation only. But then if you add small scale fading, it drops quite a bit. So you see the effect here of slow fading in a real, or at least a pretty realistic model for an environment. So next up, I'm going to show you how to actually build codes that do pretty well. But try this out and then go to the next unit.